In this lesson, we will investigate a TLS 1.2 connection with Wireshark. As a short recap, the overall objective of a TLS handshake is the construction of a secure channel from an insecure channel between communicating peers such as a client and a server that have never met before. Each TLS 1.2 connection starts with a handshake. The first stage within a TLS 1.2 handshake is the stage where the client and the server agree on a specific TLS version and a specific cipher suite to use for the connection. Once the TLS version and the cipher suite are agreed on by the client and the server, the peers are authenticated. In TLS, the server is always authenticated and the client is only optionally authenticated if explicitly requested to do so by the server. Sandwiched in between the authentication of the server and the authentication of the client is the step where the client and the server agree on a master secret. The handshake is then finished with a pair of finish messages with which the client and the server give each other assurance that both successfully executed the handshake and that both arrived at the same master secret. What we will now investigate in this lesson is the TLS 1.2 connection to the web server serving the site ibm.com. Using Firefox to retrieve the ibm.com website, it's clear that Firefox is happy about the security of the connection, as the connection to the IBM web server used TLS 1.3 with a 256-bit security provided by AES and the Galois counter mode of operation GCM. For the actual investigation of TLS 1.2 with Wireshark, OpenSSL instead of Firefox will be used, as OpenSSL allows to retrieve the IBM.com website with TLS 1.2 instead of TLS 1.3 that Firefox ends up using. Additionally, OpenSSL allows to record all client secrets generated and used for the connection, and these client secrets can then be used later on to undo all the encryption that took place within the TLS 1.2 connection. So after closing Firefox and firing up Wireshark to monitor the network, I then started the OpenSSL built-in client and instructed it to open a TLS 1.2 connection to IBM.com on port 443 and to log all the client secrets of the resulting connection in the indicated keylog file. As the TLS 1.2 connection succeeded, the OpenSSL client could then be given commands, and I was sending a simple HTTP GET request for the main index site hosted on IBM.com. After receiving the response, the OpenSSL client then closed the connection. Moving back to Wireshark, there was clearly quite a bit of TLS 1.2 network traffic recorded in the capture file. As expected, the first TLS 1.2 message recorded was then the client hello message. Drilling into this client hello message, we then first get to see the TLS record layer header of the message, where the version field indicates that this is a TLS version 1.0 record, which may be a bit confusing, but is actually correct, as the TLS record layer hasn't changed since TLS version 1.0. Drilling then into the TLS handshake protocol message contained within this TLS 1.0 record message, we then get to see with the version field indicating TLS 1.2 that the client asked for a TLS 1.2 connection. Following the TLS version indicator is the random structure, which contains the 128-byte random value generated by the OpenSSL client, and then a few lines just below is the list of cipher suites that the OpenSSL client offered the IBM.com web server to choose from. This list of cipher suites is sorted according to the preferences of the OpenSSL client. The first cipher suite is then, for example, a cipher suite providing 256 bits of security by using AES behind the GCM block cipher mode of operation, and where the client and the server conduct an elliptic curve-based Diffie-Hellman key exchange, and where the server will authenticate itself by means of an ECDSA signature. Towards the end of this list, we then have cipher suites making use of static RSA-based key exchange and AES behind the CBC block cipher mode of operation, and even use SHA-1 for the pseudorandom function PRF that's used to derive the AES and HMAC keys from the agreed-on master secret. So clearly, the cipher suites at the end of this list are the less preferred ones. The next TLS 1.2 message in the connection is then the server hello message. Drilling into this server hello message, we then see that the server acknowledges to use TLS version 1.2 and that also the server sends a random 28-byte value, again contained within the immediately following random structure. Then, within the cipher suite field, we see that the server indeed chose the first cipher suite offered by the client in the client hello message, and it's with this that the client and the server now have agreed on both the TLS version to use as well as the specific cipher suite to use. The next TLS 1.2 message is then the server X509 certificate, which is actually a chain of certificates, where the first X509 certificate is the server certificate of the web server IBM.com, and where the second certificate is the certificate of the issuer X509 certificate authority, which in this case seems to be DigiCert. As the IBM.com server doesn't ask for the client to authenticate, the next TLS 1.2 message in the recording is then the server key exchange message. This server key exchange message first contains the server ECDHE half key, which in this case is just a point on the SEC P256R1 curve. This server key exchange message is then signed by the server with an ECDSA signature, as was initially already specified by the agreed-on cipher suite. The server then sent its server hello done message, which is a message that I omitted in my presentation due to space constraint on the slide, but with the server hello done message indicating that the server has sent all of its initial server handshakes messages. The next TLS 1.2 message in the recording is then the client key exchange message, which is then the client half key of the same type as the half key of the server sent before, which for this connection is a point on the SEC P256R1 curve. The client here then followed up with a change cipherspec message, which I omitted in my presentation again due to time and space constraints, and which is actually not part of the TLS handshake protocol, but the TLS change of cipher specification protocol. Sending or receiving such a change cipherspec message within TLS indicates that as of this point within the TLS connection, subsequent records will be protected under the newly just negotiated cipher specifications. Having the client send this message at this point makes sense, as with the client just having sent its half key to the server, new cipher specifications have just been agreed and new keys have just been established within this connection. Then the last handshake message of the client is the finish message, which as we know is an encrypted message, encrypted under the just established cipher specifications and keys derived from the agreed-on master secret. This finish message is crucial, as the finish message contains a value derived with the PRF pseudorandom function from the master secret and a hash of all the handshake messages. A correct finish message will then allow the server to conclude that the client arrived at the same master secret and that the client and the server both witnessed the same handshake. However, if we try to look into this packet with Wireshark, it's then clear that this finish message is indeed encrypted and that Wireshark can't display the content of this finish message. The next TLS 1.2 message up in the recording is then a new session tickets message sent by the server. This new session ticket message contains a session ticket that the client could next time use in order to try to reuse the master secret of the current connection. This new session ticket is then followed up by the server with a change cipherspec message to indicate that all subsequent records will use the just established cipher specifications and keys. The last message of this TLS handshake is then the server finish message, which, similar to the client finish message, is encrypted as well, which then of course means that Wireshark can't display the actual content of this server finish message. This server finish message concludes the TLS handshake, and if we look a bit further down in the recording, we see that there are a few TLS 1.2 application data messages recorded as well. These messages correspond to the HTTP GET request for the IBM.com website I sent through the OpenSSL client. But looking at them with Wireshark again makes clear that these are TLS application data messages that are now encrypted under the just established cipher specifications and keys, and with this, Wireshark then of course can't display the actual content of these application data messages. What is now quite cool is that the OpenSSL client kept a log of all the client secrets generated for this TLS 1.2 connection. If we then feed these client secrets into Wireshark, Wireshark will be able to decrypt all the encrypted messages exchanged, which are then, of course, all the application data messages, but also the client finish message and the server finish message exchanged within the handshake. Looking now, for example, at the server finish message, we can see that Wireshark can now indeed display the data value contained within this server finish message. Looking then at the application data message, we can see that Wireshark now indeed can also display the HTTP GET requests I sent through the OpenSSL client before. With this, we reached the end of this lesson on how to investigate TLS 1.2 with Wireshark, which is a lesson that also allows us to conclude that Wireshark, with its TLS decryption functionalities, is quite a handy tool when working with TLS.